Good morning, friends. Today we are discussing on compressible flow. So here we are discussing some basic concepts of thermodynamic relations. So first one is our equation of the state. So we are taking here Boyle's law. So which states that PV is equal to RT. So it is the equation which gives the relationship between the pressure, temperature and specific volume of the gas. P is the absolute pressure, so that is in Newton per meter square. V is the specific volume here, so that is volume per unit mass. So your specific volume is reciprocal of your density, so that is 1 by rho. So T is the absolute temperature, so that is 273 plus T degree centigrade. So R is equal to gas constant. So that is 287 joules per kg Kelvin for the air. So in place of volume V, we are substituting the reciprocal of density. So V is taken as 1 by rho. So it is P by rho is equal to RT here. Then expansion and compression of the perfect gas. When expansion or compression of a perfect gas takes place, the pressure, temperature and density are going to change, and these changes are brought by the two process, so that is isothermal process and adiabatic process. In isothermal process, we say that the gas is compressed or expanded, so with the temperature is kept constant. So PV is equal to RT. So where R is the gas constant, T is also constant. So the product of R and T is also constant. In place of V, we are substituting 1 by rho. So it is P by rho is equal to constant. So if you take the adiabatic process, here we say that the compression or expansion of a gas is taking place in such a way that the gas neither gives the heat to its surroundings nor it takes the heat from the surroundings. So we have the equation P into V to the power of small k, that is equal to constant, where k is the ratio of the heat at the constant pressure to the specific heat. So at the constant volume, so Cp by Cv, so that ratio is 1.4 for the air. So the equation in adiabatic process is Pv to the power of small k is equal to constant. Then we have the basic equations of compressible flow. So we have the continuity equation. So the continuity equation, what we studied in fluid kinematics, states that the equation is based on the law of conservation of mass, which states that matter cannot be created nor destroyed. So the continuity equation says that rho into A into V is equal to constant. So here we know that the density is equal to mass by volume. So mass is the product of density into volume. So we have here rho into A into V is equal to constant. So differentiating this equation, rho AV is equal to constant on both sides. So it is the differentiation of rho into AV is equal to differentiation of constant is 0 here. So we have rho into, okay, so it is d into AV plus AV into d into rho. So taking both this rho and this AV as the variables here, so that is equal to 0. So rho into, okay, we have this differentiation of AV, so that is A into dV plus V into dA plus this AV into d rho is equal to 0 here. So just I have differentiated this. So this is having the next step as rho into A into dV plus rho into V into dA. So just multiplying these two terms by rho plus AV into d rho, that is this term is equal to 0. Now dividing, because we have rho A and V in all the three terms, so dividing by rho AV on both sides. So we have here rho and A gets cancelled in the first term. We have dV by V, and then in second quantity we have this dA by A. So that is rho and V gets cancelled. Only A remains in the denominator. Then when you take the third term, AV get cancelled with AV here. So rho remains in the denominator. So we have three terms here. So that is dV by V plus dA by A plus d rho by rho is equal to 0. So this is the equation of continuity. So then we have Bernoullis equation. So we know the Bernoullis equation in fluid dynamics, which is the sum of the three heads, that is the pressure head plus kinetic head plus datum head is 0. So the flow of a fluid particle along the streamline in the direction S is considered here. To write so the equation dP by rho plus VdV plus G dz is equal to 0 here. So we are making the pressure and density to get involved in the equation. So integrating each term, we have integration of dP by rho plus integration of VdV plus integration of G dz is equal to constant. In the case of compressible flow, that is when the flow is compressed, my density is not constant. But when we take the fluid dynamics, we take the fluid is incompressible fluid. So that is the ideal fluid. In that case, density was taken outside the integration. We'll have only dP inside the integration. But now since here the flow is considered as compressible flow, so the density, if the flow gets compressed, that means density is not same, so it is not constant. So with the change of density, the pressure P also changes for the compressible fluids. So this change of P and rho takes place depending upon the type of the process during the compressible flow, whether the flow is taken place as adiabatic process or this one isothermal process. We have P by rho is constant, so that is equal to C1, right? So because we have here, so that is if you take this, right? So the equation, so P by rho is equal to constant. So we have here C1. So that is constant. So we can write this rho is equal to P by C1. So integration of this dP by rho is equal to integration of dP. In case of rho, we are substituting P by C1. So C1 goes up. So we have C1 log P of E. Substituting and dividing by G, will have this equation. P by rho G of log P plus V square by 2G plus Z is equal to constant. So this is Bernoullis equation in case of isothermal process.